In this video, we're going to talk about delay, loss, and throughput in networks. So, how do packet loss and delay occur? Well, packets are going to queue up in router buffers. And if the packet arrival rate to a link temporarily exceeds the output link capacity, the packets have to queue up and wait for a turn. It's like you going to a bank, okay? If people are coming into the bank faster than the tellers are able to serve them for a short while, what's going to end up happening is that you're going to have a queue build up in the bank, okay? If people keep coming in faster than the tellers are able to serve them, what ends up happening is that that line, that queue basically fills up, and people get to the door of the bank and they realize it's too full and they turn around and leave. Now, when a packet is being transmitted, it's going to experience some delay, and when it's queued up, it also experiences some delay. Okay, and if you have certain buffers, okay, memory if you would, and if a packet arrives and there's space, it can be queued up, otherwise it is lost because there's no more space to queue it up. So the total delay at the node consists of the processing delay plus the queuing delay plus the packet transmission delay plus the propagation delay. So the nodal processing delay is the time it takes to check for bit errors, determine what output link you're going to use. Typically, this is less than a millisecond, okay? Sometimes, so in a microsecond range. Then you're going to have a queuing delay, which is the time it takes waiting at an output link for transmission. And typically, this queuing delay will depend on how much congestion a route is experiencing. Now, so we've covered the processing delay and the queuing delay. So now we need to talk about the transmission delay and the propagation delay. Okay, so the transmission delay, given a packet of length L bits and a link rate of R bits per second, the transmission delay, as we have already said, is L over R bits per second. The propagation delay, on the other hand, given a link of length D meters and the propagation speed in the medium of that link, S, okay, then the propagation delay is simply D over S. So if you want to think in packet terms, a propagation delay is the time it takes for one bit of a packet to go from one end of the link to the other end of the link. Okay? Transmission delay, on the other hand, is the time it takes to put all the bits in a packet onto the link. Okay? That's your transmission delay. Now, it should be quite obvious to you that the transmission delay and the propagation delay are very different. So to illustrate this, I'm going to use this example. So let's say we have a caravan with 10 cars, okay? Now, these cars can instantaneously accelerate from 0 to 100 kilometers per hour, and they maintain that speed between the toll booths. Okay, these toll booths are 100 kilometers apart. Now, this caravan, each car in the caravan would represent a bit, okay, and the caravan is similar to a packet. So the question then is, how long would it take until the caravan, from when it is lined up at this second toll booth, okay? So this is the first and the second. Now, the time it takes to push the entire caravan through the toll booth onto the highway is going to be 12 times 10, right? Because the toll booth takes 12 seconds to service each car. That's basically the bit transmission time. So if you want the packet transmission delay, is the 12 bits or 10 bits in the packet, sorry. So it's going to be 10 times 12. That gives you 120 seconds. Now, the time it takes for any car in the packet, in the caravan, to go from one toll booth to the other is simply 1 hour. How did we get 1 hour? The toll booths are 100 kilometers per hour, 100 kilometers apart, and the cars take travel between the toll booths at 100 kilometers per hour. Okay, so it's going to take 1 hour to go. So the time it takes from the last car basically to go from the first to the second toll booth is 1 hour, and it's going to take a total of 62 minutes from when we start, the first car goes through the toll booth until the last car arrives at this second toll booth, right? 2 minutes, that's 120 seconds for the entire caravan to go through the toll booth, and 60 minutes to travel between the toll booths. Okay, so now let's look at another example now where, let's say, the cars can now instantly accelerate at 1,000 kilometers per hour. Now, let's now say that the toll booth can service each car in a minute. So the question then is, will cars arrive at the second toll booth before all the cars have been serviced at the first? Yes, they can. See, after 7 minutes, okay, your first car will arrive at the second toll booth. Why 7 minutes? Because it takes 1 minute to go through the toll booth, and then it's going to take 6 minutes. That's 100 kilometers divided by 1,000 kilometers per hour. It's going to take 6 minutes to go between the two toll booths. So after 7 minutes, the first car has arrived at the second toll booth. But guess what? There's still 3 cars waiting to be serviced at the toll booth, the first toll booth. Okay? Now this can happen on the internet, okay? Where this is simply a case where your propagation delay basically is less than the transmission delay. So let's look at this plot to show what queuing delay looks like. So given a rate link bandwidth of rate r bits per second, a packet of length l bits, and a being the average packet arrival rate, okay? So traffic intensity is a way basically of capturing the load, if you would, okay? So if the traffic intensity LA over R is close to 0, the average queuing delay is small. This is like you going to the bank when the traffic intensity, the customer intensity, not that many people are coming in. If not that many people are coming in, right, you get to the bank and the tellers are free, you get to see a teller very quickly, very little or no queuing delay. Okay? As L over the traffic intensity approaches 1, okay, your average queuing delay becomes very large, as you can see on this plot. Okay? And if LA over R is greater than 1, it basically means you have more work arriving than can be serviced. At that point, your average delay is infinite. So, you know, these pictures illustrate this, okay? This picture over here basically illustrates a case where your traffic intensity is very low, right? So, you know, you're traveling on a Sunday morning, for example, in Jamaica. It's very easy to get, you know, places. You don't encounter much traffic. This may probably show you a picture of, you know, when you're trying to travel and there is, you know, a lot of traffic. Say you're trying to leave Kingston the last Friday before a long weekend. You might see something like that. Lots of people might have that very same idea. So you might get stuck in traffic on a highway, say the boulevard, trying to leave Kingston. Okay? So what do real internet delay and losses look like? Well, you can use a trace route program, which will provide a delay measurement from a source to a destination along some end-to-end internet path towards the destination. In its default implementation, traceroute will send at least 3 packets for each router I on the path from source to destination. Okay, so that the source knows when it sent out that packet, it knows when the packet came in, it can compute a delay. So it sends 3 packets for the first hop, 3 probes for the second hop, 3 for the third, and so on. So here's an example, a trace route that was done from University of Massachusetts to some computer in France. And you can see the 3 measurements here. So the first hop was the CS gateway, CSGW, and Gaia was able to reach that in 1 millisecond, 1 millisecond, and 2 milliseconds. Okay, some other border route at the University of Massachusetts, it was able to get to that, you know, very quickly as well, and so on. You can see with you know, line 8, you encounter a transoceanic link. How do we know that? Well, because your delay jumped from about 22 milliseconds to 104 milliseconds. That basically tells you that, you know, this machine that's represented by line 8 is relatively far away from the one that's represented by line 7. Okay, because the delta, the change in the delay is very significant. You can see the change, say, from 8 to 9 is very small again. Again, that represents that those links are, those machines are not that far apart. Now, sometimes when you do trace routes, you might get an asterisk, which basically means you get no response. The probe was lost or a router is not replying. I should point out these days that many hosts, many networks have now blocked trace routes. So it's quite rare that you get responses to trace routes. Just to highlight that, I am going to show you here. I tried to do a trace route to gaia.cs.umass, and you can see that on this network I'm unable to do that. Okay, I'm going to get several asterisks, as you can see. Okay, and this carries on all the way to the end. So I'll stop that. Okay. Now, packet loss will occur if a queue, basically the buffer preceding a link, has finite capacity, and if a packet arrives to a full queue, it is dropped. Now, this lost packet may be retransmitted by the previous node or by the source end system, or it may not even be transmitted at all. Now, questions that might come up. Another question that comes up is throughput. Okay, throughput is simply the rate that's measured in bits per time unit at which bits can be transmitted between a sender and the receiver. Now, this throughput can either be instantaneous or average. Okay, the instantaneous throughput is a rate at a given point in time, whereas the average throughput is a rate over a much longer period of time. So say we have a server with a file of length f bits that is going to serve to a client, and the server is connected to some intermediate router with a link of capacity r sub s bits per second, and then the intermediate router is connected to a client by some link of capacity r sub c bits per second. Okay, so you can think of the server as sending the bits as a fluid into a pipe, and that pipe can carry traffic at some rate r sub s bits per second, and the intermediate router will inject its traffic into a pipe that can carry fluid at some rate r sub c bits per second. Okay, so question then we can ask is, what is the average end-to-end throughput? So let's say r sub s is less than r sub c. Okay, that basically means the server is connected to the intermediate router by some link of smaller capacity. In that case, then the bottleneck link is going to be r sub s. Okay, the end-to-end throughput is going to basically be limited by r sub s in this first case. If, on the other hand, r sub s is greater than r sub c, then the average end-to-end throughput is r sub c, because that is the throughput that constrains the end-to-end throughput. And so that brings us to the point of a bottleneck link. A bottleneck link is simply a link on some end-to-end path that will constrain the end-to-end throughput. So let's say we have a scenario. This is typical on the internet. Okay, we have several clients, let's just say 10 for argument's sake, okay, connected to several servers. Let's say, maybe 10, okay? Then that link in the network core here is now shared by, all those 10 connections, okay? So the end-to-end throughput is a minimum of r sub c and r sub s and r sub r over 10, right? We assume that we're sharing the bottleneck link in the network core equally, okay? And so that then becomes the end-to-end throughput, this minimum of r sub c, r sub s, r over 10. So that brings to an end this video. In the next video, we will talk about layering and service models. Thank you.